So we're going to take a look at infinite limits in this video. We've studied functions before, like the one you see here, f of x equals 1 over x. Right? It's a rational function. It's got a vertical asymptote at x equals 0. Right? And we've learned before that when you graph that function, the y values, the closer you get to that vertical asymptote, go up to positive infinity or negative infinity. So we did learn one-sided limits in the last section, in the last video, right? When you see that little plus or minus up in the air, right? That's when you know that you have a one-sided limit. So before we deal with the two-sided limit, let's take a look at the one-sided limit, as x approaches 0 from the right? Since we have a picture in front of us, we can think about x getting closer and closer to 0, right? The y values are going up without bound, and there really is no limit here. And in previous sections, we would have said does not exist. And technically, the limit still does not exist, but we do have a notation we can use. We can say that the limit is actually positive infinity. So you don't have to say positive when it's not positive, when it is positive, but it's always helpful to kind of think about that it could be positive infinity or negative infinity. Right? If we approach 0 from the left, right, the x values are getting closer and closer to 0 from the negative side, then the y values of this function are getting larger and larger as a negative number, and we would say, therefore, that that limit is negative infinity. Now, just like we learned in the last section, when the two one-sided limits don't agree, right, we still have to say that the two-sided limit doesn't exist. Okay. Now, it's great when we have a picture. This is a very common function that we might know already. But if we didn't have a picture, we'd have to maybe explore this numerically. Right? And you could think about numbers like 1 over 0.01, right, which would be 100. You could think about numbers like 1 over 0.001, which would be 1,000. Right? And with some numerical explanation, you could start to see that the smaller, the closer to 0 the denominator gets, the larger the entire fraction gets. If we had a function like this, g of x, right, then in this case, it doesn't matter whether you're coming from the left or the right, the y values in both cases are going to be going to positive infinity. Right? So the left-sided limit would be positive infinity. The right-sided limit would be positive infinity. And therefore, we could say the two-sided limit is also positive infinity. But again, this is important to know how to do even if you don't have a graph in front of you. Okay? But we know that when a function, the x-coordinates approach a vertical asymptote, then the y values are going to head off to either positive or negative infinity. Before we had limit notation and definitions, we had a slightly different way to define vertical asymptotes, but now we can talk about the definition of a vertical asymptote. And you can see that a vertical asymptote would be a vertical line x equals c, that if f of x approaches infinity, right, as x approaches c from the right or left, then that makes this a vertical asymptote. Right? It's also clear from what we've been studying that a function is not continuous at c, even in the case where the two-sided limit was positive infinity. Remember that infinity and negative infinity don't actually exist in order to be limits. So we can say the limit is infinity, but the limit still technically doesn't exist. We're just doing better than saying it doesn't exist. Right? Saying a limit doesn't exist doesn't really tell the whole story. So when we can say that a limit from one side or the other, or a two-sided limit, is plus or minus infinity, right, that's much more useful. Now, back when you learned vertical asymptotes in college algebra or pre-calc, we generally thought about looking at the denominator. Right? Whenever the denominator was 0, that's usually where we had our vertical asymptotes. Right? But we've seen a lot of cases so far this semester where the bottom was going to 0 and the top was also going to 0, and those turned out not to be infinite limits. So if you look at the more careful definition of a vertical asymptote in the theorem discussed here, right, the top is not 0, but the bottom is 0. and there exists an open interval containing c that the denominator is not 0, meaning that the denominator is not 0 over a large interval. It's just is not 0 at a single point, right? That's the definition for a vertical asymptote. So in the past, right, we had come across situations where we had f of x, right, over g of x, and we spent a lot of time looking at the particular cases where the top was going to 0 and the bottom was going to 0, and none of those turned out to be vertical asymptotes, right? Vertical asymptotes are going to come when the bottom is going to 0. Oops. Right, but the top is not going to 0. Okay, so it's not going to be enough to just look at the bottom. We're going to have to look both at the numerator and the denominator to determine if we're looking at a hole in the graph like we saw a few sections ago, or if we're looking at a vertical asymptote. So if we do want to look for vertical asymptotes for a function like this one, right, we're going to start with the denominator. It's pretty easy, hopefully, at this point, if you reviewed your factoring, to see that the denominator factors using a difference of squares, right? But we also have to look at the numerator, and this is one of those trinomials, right? We're going to need two numbers that multiply to 8 and subtract to 2, right? So we're going to go x plus 4 and x minus 2, right? And if we write h of x in its factored form, right, it turns out that we don't have two vertical asymptotes, right? While there are two numbers for which h of x is not defined, right? One of them, as we learned before, is a removable point of discontinuity. So in this case, we would say the vertical asymptote is just x equals -2. So it's important that we think about the numerator as well. If you took the limit as x approached +2, the top would be 0, the bottom would be 0. We'd be able to resolve that and get a finite value for that limit. So what do we do when we don't have a picture, right? We could sort of imagine, in this case, that we have a vertical asymptote at x equals 3. Both of these functions that you see here, x minus 8 over x minus 3, it's the same function, right? It's already simplified, so we know that there's no 0 over 0 case, but it's always a good idea to check. You know, the bottom's going to 0, right? The top is going to -5, right, as x approaches 3. When you see the denominator going to 0 and you see the numerator not going to 0, right, you already know that the answer is going to be either positive or negative infinity, right? So we have to do a little bit of exploring to figure out, in fact, based on which way x is approaching 3, right, whether this will be positive infinity or negative infinity. Now, there's a couple different ways you can go about this. If you take a look at x approaching 3 from the left, that really means that x is less than 3, right? Which means that x minus 3, which is what the denominator is less than 0, right? That means that even though the bottom is approaching 0, right, it's approaching it from the negative side. And if you take a look at this fraction, when x is just to the left of 3, the bottom will be just to the left of 0, or negative. The top will be close to -5 as well. So we'll have a negative over a negative, and we could say that this is positive infinity. So you can use this inequality, right? We started with the fact that if you're approaching x, if you're approaching 3 from the left, you're less than 3, right? And then you try to get that denominator and figure out whether that denominator is negative or positive. Remember that being less than 0 is negative. So that's one of the approaches you can use when figuring these limits out. The other is to try to think about something a little bit more concrete. So we could think about x being something like 3.1, right? Again, the top is going to -5, the bottom is going to 0. The question is, are you heading towards 0 as a positive or a negative? Well, if x is something like 3.1, when you do 3.1 minus 3, right, that's going to be a positive. So in this case, when x is approaching 3 from the right, slightly larger than 3, the bottom will be positive, the top will be negative, and this limit would be negative infinity. Okay? So when you're showing or determining these limits that are infinite, when you realize the bottom's going to 0 and the top isn't, you still have to figure out the sign based on which way x is approaching the c value from the left or right. and look at the signs top and bottom to determine whether or not you have a positive infinity or a negative infinity. It takes some practice, and you should probably pick one of these ways you want to go, either with a concrete something like 3.1 or thinking about something like x is less than 3, and then it should get easier.